Okay, very good evening to one and all present here for this collaborative teaching on process architecture organized at Department of EC Engineering Institute of Technology, Nirma University. This is day 3 of this particular teaching where Professor Ardya Das of University of Wisconsin and Dr. Gokarna Sharma of Kent State University are experts. Our today's session will be 1 hour each by both the professors. First, Dr. Ardya Das, he will be talking about the Amdahl's law and its implication for the parallel programming, and he will be talking about the shared memory programming and some of the projects that you can carry it out. After 1 hour, the second session is by Dr. Gokarna Sharma of Kent State University. He'll be talking about the Power ISA introduction and the vector processing. So this is our today's proceeding. Uh, After the session by Dr. Das is over, I'll introduce Dr. Sharma at the time of his lecture. So now the floor is yours, Dr. Das.
Thanks, Dr. Gajjar, for the introduction. And good evening, all the students. How are you all doing? Is everything good? All right. So welcome to the third day's session. And today I am going to discuss about the Amdahl's law and implication. And also I will talk a little bit about our projects where we have done a lot of multi-core programming and shared memory using the architecture, shared memory architecture and all these things at a very broad overview. I will give you that where the industry is moving or where the domain is moving. And after that, Dr. Sharma will take care. And in between the transition from me to Dr. Sharma, I will give you a 10 minutes time where you have to evaluate my teaching and the material. That is very important for our quality assurance purpose. So anyway, so let's start today's lecture. So here it is. Can you all see my screen?
Not yet. Yeah, now coming.
Oh, okay. Yeah, now I believe you can see it.
Yes.
All right. So first of all, let us just have a quick recap that what we have done so far. So we have actually created this was our agenda. So first we have learned a lot of got an introduction of better and faster computing, then multi-core roadmap. Then we have learned about different types of fault joint parallelism, beginner level introduction to the map reduce concept, and analysis of parallel algorithm, and all these things. So I'm just quickly going over all the slide as I do every day, like brief overview. So we have talked about this better computer, then customizable computer a little bit, then what are all the faster, different types of definitions of faster, concurrency, parallelization, lots of guiding laws and observation, or you can say prophecies by great scientists and engineers. And we have discussed about the roadmap, that is where we are moving. And also we have we started with the concurrency and parallelism related programming. And after 1 hour today, we will be doing like Dr. Sharma will teach you about the technology and microarchitecture, mostly the hardware related things. So in fork join parallelism, we have learned a lot about Java's fork join library, where we have discussed like sequential versus parallel program, and parallelism versus concurrency, and what are the different types of example for concurrency and parallelism, then shared memory with threads and all these different things. And the other different parallelism and concurrency model also we have discussed just to give you the idea that what are different types of model. And also after that, I have also shared, if you have some kind of Java, if you want to know more about Java, I have shared the link for Java course, Java 101 and Java 202, which is available on Institute website. So please feel free to go there and read about, I mean, go over the lectures and do the hands-on practices at the same window. And then we have started discussing about different types of parallel programming. There we have learned about thread class and its subclasses, how to implement it. And then in a step-by-step fashion, we have seen how to write a multi-core program utilizing thread.start, thread.join methods, and all these things. And not only that, we have also seen what is a poorly written code and what is its implication and what is a better approach to write parallel programming. So there we have learned some of the strategies, and also I have shown you the newer version of the code. And also we have excuse me, also we have talked about the divide and conquer policy, which really work great for this type of parallel program where you have to distribute the resource to share, I mean, to different threads. Like that, where the small problem is divided into small chunks and the responsibility goes to threads. And also we have talked about the better program, like how to write a better program and how to gain efficiency. By showing the demo, I have shown you that we are gaining a lot of efficiency. And so what I will recommend, just go to those codes, go to these codes are already shared with you. So just change the array size. At somewhere you will see the array size, and you can just check, just play around with that array size, make it bigger, make it smaller, and see what is the implication. If you make the array size bigger and bigger and bigger, just check whether you are getting more efficiency when you are writing better code, something like this, instead of using start and join, always using this compute and join. So here actually, so just what I wanted to tell you, that here it is basically here actually you can check the number of the amount of element that you are actually handling. So I would strongly recommend that to open the code and just play around with this number, and then just check how much time each of these codes are taking. And also we have discussed in the last lecture that, well, although you will get better a single-threaded program may work better, but that does not mean that multi-threaded program does not have any implication. It's all only because some is not a real example, real world use case for multi-coded, multi-core program. It's just for the understanding purpose. And if you want to do more, just go over this some thread, this run function, and all these things, just change it according to your use case, and you will be doing the multi-core program. So those things are strongly recommended. So play around with the code. That's the bottom line. So anyway, and after that we have seen like how to get good results for Java fork join. What are the things that you need to consider when it comes to practical programming, the real coding examples. And then we have talked about the DAG and how to divide and conquer, how to visualize a fork join program in the form of a DAG. We talked about the map reduce part, which is kind of an abstraction provided by these type of things, for fork join programming. And we introduced map reduce as a de facto standard for parallel and distributed programming. All these different things we have learned. And after understanding of MapReduce, we have analyzed asymptotic, and we have shown an asymptotic analysis of different parallel algorithm, that how much speed up you can expect in the form of like T1 and TP. I mean, if TP, so here we have learned more about the terminologies like speed up, perfect linear speed up, parallelism, and all these things. And then we have seen like what should be an optimal TP. And so using this type of formula. And not only that, we have also discussed like if the, so in our case it is all about like order of n, and then we are using divide and conquer so that we can get order of log n time complexity. But as we mentioned, like it can take any other form of time complexity, like n square, and when you will just fully parallelize it, it will give you on the order of n instead of log n. And at that time, what should be the efficiency implication or time bound implication? Asymptotically, we have seen all these things. And based on that, we have shown you the responsibility of the framework user, like the high level developers and the framework writer. So those things we have seen already. So any question on all these different things? So that's a quick 5 minutes overview. Any question from anyone on all these different things? Okay, so if let me open the chat window over here so that I can easily see everything. Anyway, yeah, so all right, so today we are going to discuss a little bit about the Amdahl's law. So Amdahl's law, basically it is the applications in practice. So in practice, we have seen that much of the program, I mean not much, but very big portion of the program may be just sequential, and at that point of time the parallelization is basically limited by that sequential part. So what Amdahl's law says that parallelization is always restricted by the sequential part. You can add like billions of processors, but your computation will be limited by the sequential part. If 90% of the program is basically sequential, you won't get more than you will never get much speed up by using a better processor. So for example, so we here is the Amdahl's law formula, and possibly you have already know this, that T1 is let's say it's the sequential portion of the execution that cannot be parallelized, that is S, and T1 is the total time. Let's say this is S plus 1 minus S is 1. So if we get the perfect linear speed up, no memory issue, no IO wait on the parallel portion, then we can define TP equals S plus 1 minus S divided by P. That is only the parallel part is getting the speed up, not the sequential part. So the overall speed up, if you just divide this T1 divided by TP, T1 by TP, then you will get the overall speed up by using P number of processor, which is which can be given by this type of formula, 1 over this entire number, that is S plus 1 minus S divided by P. And if there are infinite amount of processor, of course you will get to 1 divided by S. So the bad news is, of course, if your program is 33% of the program is sequential, then even if you add a billions of processor, you won't get speed up over 3. It will be always 3 times faster. So spend a lot of time to write parallel algorithm. I mean, write the algorithm which can be parallelized over it. So instead of, so that's what we have done in this entire first session, that how to think a problem in a parallel way. Well, with the simple example of sum. Normal sum is just add all the elements of the array like one after another, like 1 plus 2 plus 3 plus 4 plus 5, like that. But what we have seen, if you want to exploit parallelism, you have to know the divide and conquer. Divide the array into half and step by step, and then give each small portion of the array to threads, and after that join all the result and add all the result, to join all the threads and add all the results to get the answer. So that's what we have learned. So do not, I mean, so the idea that so the bottom line is multi-core computing is not only about the number of processors or increasing number of processors. There is a big responsibility for the software developers also, and which should go hand in hand. So that's the point that you should remember. So what we have seen is that, well, that as I was saying, like multi-core computing is not only about adding the core. So here it is the percentage of core that is sequential in this x-axis, and so here each of these lines are basically showing the speed up of the things, speed up of the entire software. So basically, as you can see, if there is 0% code is parallelizable, there is no benefit you are getting anywhere. Then if there is like let's say 15% of the code is parallelism, you are getting like this. So basically, as you can see that as the number of parallel part is getting more, you can expect that it is getting more and more more and more benefit from the computation. So these are, so this is how you can get the speed up actually. So but so that's what you can expect. And well, many times, even if your program is totally parallel, let's say if it is 100% parallel also, you should not expect, being as a realistic programmer, you should not expect 100% speed up even if you have enough number of processor. That is because the thread overhead and memory issues, cache issues, lots of different things you need to take care of. So sometimes it's the framework's responsibility, sometimes it's the programmer's responsibility, how you want to do the things. For example, we have seen, actually I have worked in Hadoop and Spark. Just Hadoop is kind of a disk-based computing. Whenever it wants to spawn a thread and all these things, it keeps on reading. So it has a tendency to write the intermediate data onto the disk instead of memory. So it's the lower level of memory. So disk is significantly slower than RAM. So Hadoop is slower. And on the other hand, Spark, when the same MapReduce model, similar program is being used, Spark shows a much better efficiency, much better speed up, because Spark utilizes the RAM for the permanent storage. So these type of things can happen because of different types of programming model, because of the hardware usage, because of different types of things. So well, so these things actually depends on the framework to framework and their motivation basically. So for example, like, well, Hadoop is in terms of speed up, as I told, Spark is much better than Hadoop because Spark only uses RAM, but Hadoop uses disk also. But on the other hand, if you see, Hadoop can analyze significantly more amount of data with significantly less amount of resource, because it is making use of disk. Disk is less expensive, and you normally get a lot of disk space in a computer compared to a memory space. So Hadoop is much better from more data handling purpose, and it may be in some aspect it is more cost effective. So based on the motivation and all these things, you have to know, you need to use all these different frameworks, and you need to consider all these different things. So anyway, and so basically what Amdahl's law says that, well, it does not mean that additional processors are worthless. It only says that you have to be a better programmer, you have to be a better distributed programmer, rather. You have to make a better algorithm to get the advantage from the multi-core system. We can always search for new parallel algorithms. Some tasks may seem inherently sequential, but can be parallelized. For example, an ideal example is this sum. Normally, whenever you get some numbers, you just start from the left and go to the right. That's kind of like inherent parallelism, inherent thought process in our mind. But well, whenever it comes to multi-threaded, you have to think a little bit differently, like divide and conquer type of thinking. So that way the computational advantage can be exploited, the multi-core can be exploited. And we can also change the problems we are trying to solve, and or pursue the new problem. For example, like video games or CGI use different types of parallelism, and well, every day the computation processes are changing. Lots of new different algorithms are being proposed, lots of new different hardwares are coming into market to exploit these type of parallelism. And that's the beauty of Amdahl's law. It shows the limitation to the community, and community is still trying to overcome it again and again and again. And the series of innovations are being proposed, series of publications are coming, series of new hardware are coming, series of new software programming model are coming, and the entire community is making progress. So that's what the Amdahl's law. And since we are talking about these things, so let's just talk a little bit about the programming model, which actually changed the multi-core, which are revolutionary from the multi-core computing perspective. These big data programming model, they were introduced in the last decade, starting from 2008 onwards. Lots of framework came to facilitate the distributed program and multi-core program. Using this type of programming models, what you can do, so these programming models comes with their counterpart, open source version of framework. Once you install that framework, what you need to do, you really do not need to go into the detail of this fork join type of parallelism. You may not, as an application developer, you may not need to write down the nitty-gritty details of thread management and all these things. It is most of the time, it is a similar process done again and again and again. And that's where these programming model softwares are working. They are called sometimes middleware. They are taking care of the threading models and the distributed computing, which are really hard to do actually, but kind of a regular process. They takes care of that part and abstract it away from the high-level developer and exposes some programming APIs so that you can easily focus on the business logic utilizing those APIs. It's all about the library function, and you need to install the software. So first one is this is an example of MapReduce framework, or let's say this is a Hadoop framework. MapReduce programming model example, where basically, let's say you have a big data set, big chunk of the data set. What we are doing here we are basically, dividing the entire big data set. It may be a terabytes of data set over here. So what we are doing, we are just dividing the entire data set into small chunk, let's say 128 megabytes, and like that. So those many disjoint set of data. Then we are writing our own code only inside this map function. This is the user program. Then what happened after you write this map function and if you execute the program, this user defined function, whatever you have written inside this map construct, it will be automatically executed on all these disjoint set of data. And the entire computation over here is independent of other. So the DAG does not have any type of dependency. So each set of data in parallel, utilizing the full potential of MapReduce, multiple core, they can work here. And after that, what they do, they just write some kind of intermediate result over here. And then these things are basically written in the form of a key and value type of things. And based on this group, after that, this MapReduce basically group the intermediate result on the basis of this key part and send it to this reducer part actually. So, and after this reduce is again a user defined operation which basically works on each of these group, where let's say each of these group which are separated by the key, and then write the final result on a distributed file system or something like that. So that's MapReduce, where a large set of data is divided into small chunk and then analyzed independently using this map function and write some intermediate result. And after that writing, this intermediate result is again being analyzed by a reduce function, user defined reduce function, again in parallel. And the final, this is kind of an aggregation function, and the final result is written on the computer, on the machines. So that's it. This is an example from our genomic workload. And anyway, so that's why you can see some terminology like KMR, read, and all these things. But you can think of like a normal data set. That's it. So so that's one of the programming model, MapReduce programming model. Then the other programming model is graph computation. So that's another thing. I mean, in the computational world, graph related problems there are lots of graph related problems. So graph processing is a fundamental core problem. This is basically here, this part is actually same as the map part over here. Here also the data is basically divided into small chunks, and it is just seen as a normal graph. I mean, a normal graph. Each of the chunk of data is actually being seen as a nodes in a graph basically. And on those chunk of data, it just use a worker program, just like this map here. We call it vertex program, just a different name. All right. And the main difference is, instead of writing it in the intermediate result over here, what this programming model does, it basically send a message to each of the worker to synchronize the process. So here the synchronization is being achieved by writing the intermediate data in the disk so that everyone can read it. So it's a shared space where all the map task and all the reduced task, or simply the workers, are reading the data from here. But here everything is taken care of by message passing, but in worker to worker. All the worker will have the idea of what is going on in this entire phase of computation. So that's another programming model. And in this way, actually, it basically progress. Each of these things are a step, and each after all the workers are in sync, that is, it knows all the what is going on in all the other worker, it moves to the next step, and this way the computation proceeds. So that's kind of the distributed vertex-centric computing, which is called there are several frameworks like Giraffe, Graphics, like this, and modern distributed, modern deep learning frameworks also you can think of like this, which are like TensorFlow, PyTorch. They are also seeing the entire program as a graph processing problem. So that is another thing. And then there is something called the distributed NoSQL, which also leverages multi-core computing to enable the search process. The programming model wise, the difference is it is basically instead of doing some batch processing, it is doing the query. And the other difference is here actually everything is a shared nothing architecture. So for example, this chunk of data is only available for this map. This chunk of data is only available for this map. So this is kind of a shared nothing type of architecture in followed in Hadoop MapReduce. All right, and there can be other different MapReduce in other different framework, but this is what is being followed in Hadoop MapReduce. Each map has their own corresponding data set. But here the thing is, in distributed NoSQL, each of the client through an application program interface of NoSQL software, it gets the global or tabular overview of the entire data set so that it can easily enable the search process. So that's one of the thing, and these are all like optimized for query processing. So based on the requirement, so query processing can be done in two different ways, like in memory and disk based, based on your requirement, based on the fastness you want or cost optimization, whatever you want to do, you have to select the framework. For example, in memory has Hazelcast, Redis, and disk-based computing has HBase, MongoDB, and all the different things are there. So these are different type of multi-core programming model. I mean, three main multi-core programming model that taken the world in the last decade. So it is as a final year BTech student or the master student, you should know about what is going on. So that's the motivation of this. And utilizing this framework, as I have told, you can easily focus on the business logic only. What should be the content of this map function? What should be the content of reduce function? What should be the content of these workers? The other threaded nitty-gritty details of the threads and distributed communication will be taken care of by the framework itself. And here you can see some name of the example framework, like MapReduce is Hadoop, there is Spark also, the distributed NoSQL is Hazelcast, Redis, HBase, MongoDB, Vertex-centric graph processing is Giraffe, Graphics, TensorFlow, PyTorch, lots of different examples are there to facilitate this computing. And that's the success of multi-core computing. After introduction of these frameworks, everyone could write multi-core programs. So these things are revolutionary. And so, I mean, these things actually were introduced to address Amdahl's sequential program. So without these framework, it was not very easy to come up with a fully parallel algorithm. Now, once the community got this type of construct, now it became very easy for many people to write parallel coding and to visualize what is going on, what is the fact, and figured out lots of different things and came up with different parallel algorithm easily, just by focusing on the business model. So that's the beauty of Amdahl's law. And this is how the community is responding towards the limitation of Amdahl's law. The community is trying to overcome using this way. And not only the software model, but the hardware is also revolutionizing. So if you check Wikipedia or anywhere, if you search over internet, you will see that the processor, storage, network, everywhere the bandwidth is increasing and the cost is decreasing. And this is every day the performance point is being changed. And that's why, let's say this IBM Power 8 architecture was obsoleted, and then Power 9 came. Now Power 9 is improved to Power 10, and lots of different things are happening. So overall, the bandwidth is basically increasing. It may be the computational bandwidth, it may be the memory bandwidth, it may be the network bandwidth, everything, storage bandwidth, everything is increasing, and the performance points are changing every day. Yesterday, what was great performance, today it's not a big performance at all. Tomorrow the technology is just obsoleted and the new technology is replacing everything to take the advantage. So it's a constantly evolving process. And these are some of the hardware where I have worked personally. So for example, so these are all distributed computer hardware. For example, the first one is basically a Cray computer. This is a small box, and inside this small box, basically there are 7 different computers are there. these are small, these are called blade servers. So inside here, basically there are 7 different boxes, and those are full-fledged computer. Each of these machine, each of those 7 boxes has like 32 gigabytes of memory, 2 Intel Xeon for 8 core processors, and each of these node has like 128 gigabytes of disk space, and there are 7 of these, and each of these things are actually connected using the normal Ethernet cable. So that's a blade server type of things. It's not very high performance, but it's good. It can easily run distributed program and can do proof of concept type of work if you work on the big data domain. The next one is a super MIC computer. It was in LSU, where Gokarna and I or our PhD, and that was a very nice supercomputer, which where each node is has like how much 64 gigabytes of memory, and like it they 16 core Xeon processor, Intel Xeon processor, and like each node was equipped with 500 gigabytes of hard disk space. And I cannot remember the exact number of compute nodes that are available in this cluster, but it's like it's in the range of 100, 500, something like that. So here basically each of these slots that you can see over here, they are each of them is a server computer, and these purple color things that you are seeing, those are all network using which they are all connected. So if you get a very big problem, you have to develop a distributed multi-core algorithm for that, and then deploy in this cluster. Lots of different computers will work together to give you the result back. So that's how the thing works. Then, so that's another supercomputer. This is a supercomputer. And after that, this is another type of distributed computer, which is developed by Samsung. I mean, here also there are like, so this is a different type of thing. So this is a scale out system in the box. So here actually, as you can see, these small slots, so these sleek slot that you can see, they are all self-sufficient computer. Each of them has like one core processor, and then there is just 64 gigabytes of memory, very powerful computer, each of these sleek slot, and one NVMe type of SSD, which is very fast IO storage. And each chassis used to have like 24 slots, I think, if I can remember properly. So that's a very nice cluster. So it used to be there, like I mean, its name was Series 2 when I did our research, and we have published multiple papers based on this architecture and all these things.
So, Dr. Das, at the back in the chassis, does it use the InfiniBand for the connectivity?
Well, no. So in here, right? In this one, or which cluster are you talking?
So the previous as well as the last that you talked about.
Oh, okay. So yes. So in Super MIC, what you can see here, it is using InfiniBand. InfiniBand with 2:1 blocking ratio.
Okay.
That's what. And here actually the connection is totally different. It's not using Ethernet. It's neither using Ethernet nor using InfiniBand, but it is a PCIe Express. I mean PCI Express based connection connecting all these slots. So that's a good question. Thanks. I should have told that. Anyway. So that's another type of cluster. And then this is the fastest supercomputer called Summit. I mean, Summit was the first fastest supercomputer, at least last year. I don't know whether it is now or not, but this is in Oak Ridge National Laboratory. I have used it for a few days with the help of Ganesan, actually. He managed an allocation over here, and I used to do my metagenomic workload over here. It's basically totally a power Power 9 based system, this entire system, and in the last year it was the fastest supercomputer. So these are different types of supercomputers and distributed systems are available nowadays, and as an electronic student you may find all these things very motivating and interesting also. So that's all from my side today. And well, another thing that I wanted to show you, that well, if you are interested in some benchmarking or evaluation of cluster type of things, I mean, why IBM, the evaluation between Intel and IBM processor, you can always read this article that we have published together with IBM when I was in LSU. So it is let me just share this code. So here you can see IBM's SMT8 multi-threading, how it is impacting our genomic workload. This is a cluster, 15 node cluster that we have actually, 40 node cluster that was situated in IBM New York Poughkeepsie. And here actually so here you can see the Hadoop configuration and the input data size. As you can see, we have tried to analyze almost 3.2 terabytes of data, where the intermediate data size was almost 20 terabytes and the output size was almost 8.6 terabytes. So whenever we are talking about multi-core computing and big data, we are talking about this type of scale basically. And here are all the results. Mostly we have got better performance result on Power 8, and I'm pretty sure this was in 2015, and Power 9, Power 10 can show significantly more benefit compared to that. And here you can see but anyway, you can get the fundamental idea. You can see that how the SMT, like simultaneous multi-thread thing, works in Power 8. I mean, in the IBM Power system in general, let's say. And here are all the performance differences. You can see that. So here 120 supercomputing nodes, the traditional supercomputing node was producing like, we could get better performance only using IBM Power 8 40 nodes. So now you can see the difference between the power processor and these traditional Intel based supercomputer. And so here it's like almost like, so as you can see, 6 hours on when it comes to this 3.2 terabytes of metagenomic data, 6 hours and 22 minutes on 40 nodes of IBM Power 8 cluster, and whereas it took 20 hours on 120 Intel nodes. So that is which is almost like 9x improvement in terms of performance per server that we have observed in Power processor. But I'm pretty sure in Power 10 these numbers will be even more, maybe 10 or 20x, I don't know. But this is how Power system works, and that's where actually my collaboration with IBM and Open Power started. So if you want, you can go over this paper and let me share it with you. And oops, yeah, got it. So that is it from my side. So any question? Let me see in the chat window. So why is 100% parallelization is not possible? Well, Ambika, from a software developer standpoint, I can give you the broad overview. Like, let's say there is so some software, some framework is what should I say? Let's say there are several interdependencies. So let's say sometimes there are lots of network related things and communication things are going on in the back end, which actually hinders the parallel processing. And also if you, and sometimes like, let's say lots of memory overhead issues and many different things you need to take care of, which are basically hard to take care of basically. So whenever you go for a big amount of data set, the memory access and memory access things, and then let's say these what is that, the channel, the dim channel, and they get saturated. Sometimes you need to read the data from disk, and then you have to evaluate. That also takes some time. Now this disk parallelism is not like very much scalable, just like the processor parallelism, because they have some saturation bandwidth limit. And that's why, so because of these, all these different components follow different types of hardware architecture and models, it is normally not possible to get 100% speed up. Like as many processor you will add, you won't get that much of speed up. It is most of the time bottlenecked by memory, disk, and network. And possibly Dr. Sharma can give you some hardware related things, and maybe some asymptotic analysis overview also. Yeah.
Oh, right.
Yes.
So what happens is it depends on your application. So basically, let's suppose your application has a sequential part. And then if your application has a sequential part, there is no way you could run it, even though you have 2 or more processors in parallel. So you have sequential part, you have parallel part. Parallel part, you could actually run in parallel. Okay, so if you have more processors, then you get better time, everything. But if you have sequential part, then there is no way you could exploit the parallelism that you have. You have to run sequentially. So the new design idea is you do not want to have homogeneous multi-core system of same frequency or same speed in the processors. So what you try to do is you want to come up with a system which has heterogeneous cores. So what heterogeneous cores are is you have some cores, they are more powerful than other cores. So basically the not so powerful cores are parallel cores. There are many of them. Some cores are very powerful, but there are some of them. So if you say that the processor is powerful, that means the processor is running in high frequency. When it runs in high frequency, even the sequential computation, you could get better timing because the processor will finish that sequential part faster. And then parallel part is done by the not so powerful processors, but there are so many of them, they will be able to finish them faster. So this combination is going to give you better result on variety of applications. And then so why you need to come up with this design decision is that you do not know the application workload beforehand. So you have to be ready for any kind of application workload that comes into the system.
Sure. Thanks, Ambika. Did you get your answer? All right. Thank you. So, and thanks, Dr. Sharma, for the answer. So, well, I think I am almost done with my part. And now, please welcome Dr. Gokarna Sharma, who is an associate professor of computer science at Kent State University, USA. And he's also the director of Scalable Computer Architecture and Emerging Technologies Laboratory, commonly known as SCALE, in the Computer Science Department of Kent State University. And Gokarna Sharma got the NSF Career Award, which is the most prestigious award in USA for a researcher, for his research proposal on transactional memory for distributed system. And not only the career award, but he got some more funding from NSF and other sources. One of the main was eager funding, where also he got it funded for the transactional memory foundation for distributed multi-processor system. So I'm pretty sure you will learn lots of different things from Gokarna, and you will learn a lot of hardware related issues and multi-core related things from him. And with a view on the power-based architecture. So anyway, and now before going to Dr. Sharma's session, I have something. So you have to evaluate the part that I have taught. So let me share a link which I want to do it. So that's the quality assurance purpose of Institute. So please write your unbiased comment, like where you want to introduce, I mean, which things went well, which you really like, which you did not like. So please give us the feedback, and based on your feedback we will try to improve all these things, and possibly will offer better course in future. So because it is our continuous effort. So anyway, we still have, like as I told, we still have 7 minutes to complete the survey, and after 7 minutes, Dr. Sharma, you can start after 7 minutes. So Dr. Gajjar, please encourage the students to give this feedback and all this.
Yes. I insist all the students to fill up the feedback, and as rightly said by Dr. Das, it is always for improvement. So give your true suggestions as well as the true feedback that will help all of us. We also follow the similar kind of pattern once our sessions or expert lectures are over, as well as the faculty teaching also. So the students are accustomed to that. So I request all the students to do
Perfect.
the needful. And as rightly said, I would also like to add upon that NSF, the National Science Foundation grant, as well as the awards are very important, particularly for the students. You should always look at the professor who is having an NFS grant, so NSF grant, so that you get a TA-ship and RA-ship under that grant. So it is always great. So we welcome Dr. Sharma for the next 5 hour sessions. Thank you for accepting our invitation and joining. Once again, I request all the students to complete the feedback within 7 minutes, so that we can start our next session sharp at 8.
So I have shared my full name. So please use this name for the course. I mean for instructor name, and please use this name as the course. So Arghya Kusum Das is the instructor name, and just use this thing like multi-core program as the course name. I shared it on the chat window. So please take 6 minutes, and after 6 minutes, Gokarna, you can start.
Sure. Thank you, Dr. Das. You did a wonderful job there in your session. I used to cover that part, not coming and giving the perspective. I have other lectures where I give the perspective on what is the importance of writing thread level chain memory programs and all that. So, so the lecture that we delivered is the kind of lecture that comes after so many other lectures where we build the context and then we go there and then talk about that. But still, when I start my session, first of all, I would like to talk about a project that is related to what Dr. Das covered. The goal of that is to, you learned how to write fork join parallel programs and everything. So now it's time to go and test it, So from our part, you do not need to submit that project to us, but I want to give you a project so you could go and work on if you like. Maybe it will help you to, go and try and then see what do we mean by that, and then what is parallelism, how you use threads, and then how you use fork join library. It helps in your future. It helps in if you continue further in your academic career, and then maybe that will give you a little bit perspective on how you think about parallelism, what parallelism is, and then somehow think on solving problem from the parallelism part. Maybe that will help. So I will talk about that, and then I will after I talk about that project, I'll talk a little bit about that project, and then we'll move into power architecture and open power, and then where we want to go.
Sure. And Gokarna, I may not attend today's session because I have to computing conference. I have some meeting fixed. So possibly from tomorrow, I will be in the session as in the background.
That's fine. But how did you share your screen? Did you do the share full screen, like all your screen, and then put your one, or how did you do it?
Yes, that's what I did.
Okay.
Yeah, I just did the share screen, full screen.
Share screen. Okay.
Mm-hmm.
It says can't share your screen. What does it mean?
Does it need some kind of like settings change? Are you on Mac?
Yeah, I think so, right?
So possibly you need to do that settings and then you need to check that.
System preference.
Yes, maybe.
And screen sharing. Okay, I think I got it.
All right, Dr. Gajjar and Dr. Sharma, I think students started submitting, so you can wait another couple of minutes or three so that everyone can finish it. And then Dr. Sharma, you can start, and I should take your leave now because I have.
Thank you,
Right.
Dr. Das, and we'll have a 5.
Thank you,
Yeah.
and see you tomorrow. Bye.
Yeah. Thank you, Dr. Das. So I will see you tomorrow.
See you tomorrow.
Yeah.
Okay, bye. Wishing you a great day ahead.
Dr. Gajjar, I forgot to mention, but we get some of the students from Nirma University here in our MS program.
Is it? I know that number of years before I had sent a few resumes as a recommendation. Right now, I'm not sure that currently, do you have the students?
I think some of them, I saw some of them, maybe not from not from your department, maybe
Oh
from
yeah,
other
maybe
ones.
from other department. Normally, we have 10 to 20% students. They go for higher studies. So I used to give recommendation almost 8 to 10 students every year. We have a collaboration with uh, Florida Atlantic University, then University of Southern California, then Iowa State University, then SUNY Birmingham. We have a kind of collaboration.
So we will start in 5 minutes.
Yeah, we can start, sir. The students might have submitted the feedback. So those
Okay,
students who have, yeah, we can start, sir. Yeah, please.
we can start. Okay.
Yeah, sure.
So welcome everyone. So I'm Gokarna Sharma. You know me. I'm at Kent State. I'm an associate professor here in computer science. Um, I teach multi-core computing. I teach Internet of Things. I, do research in multi-core systems, distributed algorithms. If you go online, you could see my profile. If you like what I do in terms of research, and then if you are interested in further study, you can contact me, send me your resume, or apply to Kent State, and then we can work in future as well. But I'm so glad to be here
Thank you.
to talk about something that I do every day. And so here what I do is that I'm going to take over from Dr. Dash, and then I'm going to talk about one project. So maybe this will give you some perspective on after you learn some of the skills, then how do you go and apply those skills? Okay, so this one is, so you know now how to write parallel program to sum an array, right? It's a one-dimensional array. Now here we are going to talk about two-dimensional array. Okay, so the two-dimensional array is not given to you. You have to make it an array. So we have data, and then you have to make it an array. And then after you make an array, then you have to think about, oh, from one dimension, how do you go to two dimension, and then write a parallel program. That parallel program would not just divide an array, one-dimensional array, into segments and then does the computation here. When you are working on two dimension, then when you divide the work, then you will have a smaller rectangular data that you have to deal with, or rectangular array that you have to deal with. Okay, so pretty much it's a long discussion, so it's 9 pages. So you see that the discussion is long, but do not get overwhelmed with the discussion that I have for this project, because I want to give all the details about this project and everything. That's why I do not have PowerPoint slides for this project. So basically you could go read and then try to see what this asks you to do, and then you can do it. So this project is population density. So what we're trying to do is that we are going to use the census data. So we have Census Bureau. So the data that you are using here is the United States Census Bureau data, okay, from 2010. And then it has 220,000 data points. So basically the data points are given. These data points are mapped to some particular geographical location. And then you have to use these data points, translate them into two-dimensional array, and then start writing parallel code, or the levels of programs here. So I'm going to talk about some of the versions of code that you are going to write using PorcJoin parallel framework. So you know PorcJoin framework, so you can just use the example code from the lecture or the code shared by Dr. Dash, and then you can start working from there. So here, the goal is to just expose you into different functionalities, okay? And then so here you will have simplicity and efficiency. If you look here, how PorcJoin parallelism works, or particularly Java's PorcJoin parallelism, we talk about how to solve the problem from sequential algorithm. You write sequential code and solve it. And then after you write sequential code and solve it, then you'll go and write very naive parallel code for that. After you write very naive parallel code for that, then you are going to optimize it, okay? So Here, the goal is to see how much parallelism helps in this situation. We have only 220,000 data points. So 220,000 data points is not a very good input to write a parallel code for that, because even in the sequential setting, you will have answer even before or faster than from the parallel program. And then so you might not get the benefit, you might not get to see the benefit of writing parallel code for that. But if you write well, if you optimize well, then you will get to see the benefit. That means the parallel program will perform the computation faster than sequential. So what is the learning objective for this project? So you will gain experience designing software that processes data in several stages. So here, the input is not in two-dimensional, not given in two-dimensional array. Okay, so it is given as data points, and then you have to translate these data points into two-dimensional array, and then you can process. So this mapping of these data points to two-dimensional array, it needs some thinking. So that is a pre-processing of data, not by the computation, but by the code that you write before you run parallel code. So you have to map and then make a two-dimensional array, and then that is a one-time job. And then you will write divide and conquer kind of parallel algorithm using proxy parallelism. In every stage, you first spawn a thread, and then the thread will getting all the job, and then you spawn one new thread, give half of the job to that thread, and half you keep to yourself, and then you continue doing that until you reach to a level where there is sequential cutoff. And then from when you reach to that sequential cutoff, that thread is going to do the computation within that particular sub rectangle that you are working on, and then it will compute the sum. So for the population, it's very easy. This problem is also similar to summing an array, and then sum is a very nice problem to write a parallel code, because if you sum the subset of the rectangle and then compute the sum for all the subsets of the rectangle, and then the result of them, when you combine them later, you will get the total sum. Okay, so this is like associative property or composite, or we call it. Okay? So, and then third, you will investigate a different implementation approach that requires locking for synchronization. So why locking for synchronization? You will get to know later. But what happens is, when you are working on your subrectangle, either you have to make that new rectangle and then work on, or you do not want to make different rectangle, different arrays for doing the computation. You might want to update the array, the original array. And then if you want to update the original array, then you cannot just simply go and write the data value there, because someone else might be trying to write the same value at the same time to the same location in the two-dimensional array. If that happens, then probably your data is not correctly updated, and then you might not get the correct answer. So for that one, if you are going to update some location, the update means when you are going to write some location, then you have to tell others that I'm writing now, and then only after I finish writing, then you can go and write. So that is locking. Locking means you have to say, okay, you cannot enter this particular location now because I'm working on it. So that one, you have to tell them in certain way that it will signify. So that is locking. Locking, you can maybe put one bit information there. So everyone, before they go and then try to update that location, they will go and check whether the bit information is 1 or 0. If 1, then someone is still working on it. 0 means no one is working on it. You can go and then update it. So every time you have to check. And then when you go to that location and then you write, after you finish writing, you have to switch that bit from 1 to 0, because if you do not switch from 1 to 0, then other processors think that you are still inside, and then there will be deadlocking situation. Okay, so this is locking. And experience the difficulty of evaluating parallel programs experimentally, because there might be certain situations where you find it difficult to see how things are working, because we mostly tend to think from the sequential perspective, and then when we go into parallel perspective, then some of the even very minor trivial things we just are not able to see that there is a bug or something. So you will also experience the difficulty of evaluating parallel programs. And write a report to present the interesting parameters of your implementation and how you evaluated them. So here I'm giving you some write-up questions to make a report, but that report is not necessary. You do not need to submit, but what it helps you is that you go and then try to answer some of the questions that are there for the write-up of the report. And then these questions will help you to guide you through what kind of experimentation or what kind of result that you are expecting, that you are looking, how do you compare these implementations and all that. And then maybe it will guide you through the process of experimentally producing the results and timing and everything after you've done coding the program. And then how do you know that the program is working correctly? Okay. So there are several files. So provided, let me go and show you here. There are several files. So in the project files.zip. So I will share that file, that single zip file, and then this description as well. Today to Dr. Gajar, and then Dr. Gajar will share with you this information. So there is so this particular code, there is a template for many things. For example, you can write the GUI information, the interface as well. For example, you can make a graphical user interface, and then you put the information there, and then it will give you the answer and all that. So that you can do too, but that is above and beyond. If you want to go and then do further, you can go and do. But for what I care more is whether you know the technique on writing the parallel programs or not. So the other is just the outside, it looks nice and everything, and then you do not need to worry about the details. But if you know how to write parallel program, then that would be the objective for this project. Okay. So for example, here, so this files here, for example, interaction paint.java, map paint.java, usmaps.java, usmap.jpg, continental usmap.jpg. So these are all you do not need to really understand. Okay, so these files are related for the optional graphical interface. Okay, but you do need to understand these files. For example, census data.java, census group.java, rectangle.java, population query.java, census population 2010.txt. So this file, senpop2010.txt, is the file where you have the data points. So you have to read the file. After you read the file, you have to extract the information from there. After you extract the information, you have to put that information in two-dimensional array. And then only after that, you could write parallel code that works in that two-dimensional array to solve the problem. So you might find introduction to the program framework useful. So if you click on this link, it will take you to the website where you could get to read that information. Okay, so let's talk about what your program will do. Okay. So you have senpop2010.txt. So it will be inside the project files I will share with you. It contains real data published by US Census Bureau. Okay. So if you want to know what Census Bureau does, you can click on that link. So in India as well, there is a Census Bureau, and then they count population in different geographical areas, and then the total population, right? The data divides the US into 220,333 geographic areas called census block groups, okay? And reports for each such group the population in 2010 and the latitude, longitude of the group. So if you look into the senpop2010.txt, then what information you find there is the longitude information, latitude information, and then the population at that point. So now think about the point is giving that information. Why? Because you are mapping whole US. This is a geographical area. The whole US. You are mapping that into 220,333 data points. So particularly, this data point means you are talking about one rectangle there. rectangular area, because 220,333 data points, they have to cover the whole US. Okay, so that's why one data point means some area, some rectangular area. Okay, so this latitude and longitude, what it gives is that it will give somehow the center of that area. Okay, so this the center point, and then all the population within that area is counted there in that point. That's how the data is given to us. So it actually reports the average latitude longitude of the people in the group, but it will not concern us. We don't need to worry about it. So given this data, we can imagine the entire US is a giant rectangle bounded by the minimum and maximum latitude longitude. So from the data, you can find minimum longitude, you can find maximum longitude, you can find minimum latitude, maximum latitude, and then when you find minimum and maximum longitude latitudes, then from that information, minimum, maximum of latitude and longitudes, you can come up with a rectangle. That rectangle the rectangle is of size in such a way that all the US population or all the data points, given data points, are within that rectangle. Okay, so if you look into this rectangle, what might happen? Most of this rectangle will not have any population, of course, because the Alaska is on the top, and then so when you put everything inside the rectangle, and then when you are looking into the data from longitude and latitude, then maybe most of the Canada part comes into picture as well, and then which is not counted. So basically, if you look into the rectangle that is covering Canada, then you will see population 0, because we are just looking into US census population. Okay, so the rectangle includes all of Alaska, Hawaii, Puerto Rico, and therefore, since it is a rectangle, a lot of ocean and Canada that have no US population. Okay, the continental US is not a rectangle. For example, Maine is well west of Florida, adding more ocean. Okay, so that's why. So you have this situation. And then what this project does inside, you do not need to know. Actually, it actually does the projection of longitude latitude so that the spherical latitude and longitudes are going like spherical, right? Like go like this. So that spherical situation, it translates to somehow rectangular situation. Okay, so you do not need to know, do not need to worry about that. It is written in the background. So you can just use whatever information that gives by that projection. Okay, so what you want to do when you write this code, what I like you to do is that you want to answer queries related to areas inside the US. Okay, so if I ask what is the total population, then you are counting all the population that is in 220,333 data points. When you sum the data in all the data points, then you will find the whole US population. Okay, and then when I consider these data points, then I'm considering the whole rectangle. Now I want to find the population in the subset of US. Let's suppose I want to look into the sub-rectangle of the whole rectangle that covers US, and then I want to find the population for the sub-rectangle. And then if that sub-rectangle happens to be in the New York area, probably we'll see big population there, right? If we have the rectangle that covers, let's suppose Alaska, will have a very few population. Similarly, if it goes to the Midwest of US, then probably a small population. If you go north of New York, since it covers some part of Canada and then which doesn't have a US population, then maybe you will get it small. So you can see where there is a big population and then where there is a sparsity on the population. So you can actually make different kind of observations on the data that is available there. Okay. And then, for example, here in the implementation, we always try to do the rectangular queries with, just the rectangular queries. And then if you want to go and beyond, you can have not rectangle or maybe any shape queries, right? I want to give a shape of the area, and then you could come up with an answer. But that is above and beyond. You can go and play with that if you like, but that is not required here. So what does your program do? It will first process the data to find the four corners of the rectangle containing the United States. Some versions of the program will then further pre-process the data to build a data structure that can efficiently answer the queries. The program will then prompt the user for such queries and answer them until the user chooses to quit. Okay. For testing and timing purposes, you may also wish to provide an alternative where queries are read from a second file. You can do that as well. More details on how your program should work. The file containing the input data, two integers, x and y, describing the size of the grid. Okay. And then so here, how to compute the westernmost point, southernmost point, easternmost point, and northernmost point, and then how you come up with the total rectangle. That information is there. So you output two numbers, the total population in the queried rectangle. So you will input a query rectangle, and then you will say this is the total population within query rectangle. And then you will also compute the percentage of the US population in the query rectangle, because if you consider the whole rectangle, then you will get the whole US population. And if you consider the total population within the sub-rectangle, then you will get the population within that query rectangle. So basically the query rectangle population, if you divide by the total US population, you will see the percentage of the population of US that live in that particular query rectangle. Okay, and then you repeat that. So so the interesting part is the 5 different implementations that we try to do here. So you will implement 5 versions of your program. There are significant opportunities to share code among the different versions, and you should seize these opportunities. Okay, so you write one version, and then maybe part of the code you write in that version might be useful in other part. So version 1 is a simple code that is sequential. Okay, so basically what you do is that before processing any queries, you process the data to find the 4 corners of US rectangle using a sequential algorithm. And then so this sequential algorithm takes order and time. Okay, so forget about the overhead and everything, order and time. And what is n? N is the number of census block groups. So basically order and time means you have 220,333 data points, and then it will take around that time. Then for each query that comes, you have to do another sequential order and traversal to answer the query, right? So the sub part might be in different areas, or it is also proportional to the size of US. So it again takes order n. Okay. So this is a simple sequential code, and then it will give you the answer. But every time you have to answer a query, then you spend order n time. Okay. So now we want to make it better. So we know how sequentially this problem is solved. Now you want to solve it using a parallel code. So what do you do in the parallel code? This version is same as version 1, sequential, but initial corner finding and the traversal for each query should use the fork join framework. So now you use the fork join framework and then make it parallel. For example, the corner finding you can run in parallel. In the sequential, you want to find the corners. So basically, you run one part of the code. Let's suppose you run the for loop, and then find the minimum latitude. You run another iteration, and then you find maximum latitude. You find another iteration, and then minimum latitude, maximum latitude and longitude, right? So sequential. Here, what you want to do is that you run the code in parallel to find minimum and maximum. So you know that the maximum finding, minimum finding, if some data is minimum locally in some part, then that is also minimum in the global part. Okay, so basically this is also associative, if you are doing sum or finding minimum, finding maximum, or finding whether some element is there or not, These kind of problems are very good input for a parallel program. You can write very efficient parallel programs for that. So here, the corner finding of the rectangle, actually you can run the code in parallel and then find the minimum latitude, minimum and maximum longitude, writing a parallel code. So that code will run in order log n time if you do that, okay? So, and then, so the work will remain order n because that's the total work that you have to do, but the timing or the span that Dr. Das talked about, work in span. So span goes from order n to order log n, okay? So finding the kernel should require only one data traversal, yes, and each query should require only one additional data traversal. Now, when you have a query, again you try to answer that query in parallel. So basically, you run the parallel code to find the answer for that local rectangle. So this way, you could solve this problem going down from order n time to order log n time, writing simple parallel code. Okay. Now there is a version 3 that is sequential code. This is still sequential, but this is very smart. What it does is that you do one traversal of the rectangle. You visit all the data points of that rectangle one time, and then from next time you can answer queries in order one time. So basically you are investing order n time just one time to process the rectangle one time. After you process the rectangle, any number of queries that come, every query you can answer in order one time. So this is very smart way to solve this problem, because this problem has some nature. That nature makes it very useful to write such code. And then here, if you look at it, the cost, if you amortize the cost over many query operations, what happens is that initially one time you spend order n time, and then after you spend one order n time, every time you answer the query, you are answering in order one time. So think about it. You answer n queries after you pre-process one time, and then you invest order n time. Then if you sum it, the total is going to be order n plus n times order O1. So that will be 2n over n. So this is in constant time. In total, amortized time over for many queries is going to be down. But in the parallel code that we have written up, then every query, you know that you can answer in order log n time. Okay, so that's the smarter way of doing, although being sequential. So how does it do? So the first step, you will have this. Okay, so you have agreed data per the position. Let's suppose you have one point which has population 0, another point population 11, another point total population 1, another point total population 9. So here, this example given is 4x4 grid. Okay, so the rectangle which has 4 elements. In x-axis there are 4 4 rows and 4 columns. Okay, so your data will have 220,000 data points. That means it's very big, but this is just for example. So let's suppose the population is represented as 4x4 rectangle, and then you have this population in each of the points on the grid. Okay, so 0, 1. Then in step 2, what you do is that in the step 2, you will do this computation. See here, so you start from here. So this is 0, and then if you go here, this 1, then you sum 0 plus 1, and then that is 1. Okay, and then let's suppose here 3. This is 3. This 3 is summing 0 plus 1 plus 2, the top 3. Okay, that gives 3. When you go here on the 4th, it has 9. So sum everything up on this column, 0 plus 1 plus 2 plus 9. So that will give you 12. Okay. And then the next one, let's suppose here this 11. So this 11, when you go here in the 11, then you are summing this 0 plus 11. That is 11. Okay. Now the interesting part comes. let's suppose this 19, right? How is this 19? This is 19 because now you are looking at a rectangle, sub-rectangle that is 0, 1, 11, 7. Okay, so this 7 here, what do you do is that think about a rectangle on the north, north left corner, covered by 7. Okay, so here if you look into this one, so the top is 11 and then the side is 1 and this is 7 and then the leftmost is 0, right? So basically you are summing up these ones, not this one, 0 and 11 and 1 and 7. So that is the subrectangle. Okay, so when you do that you will get 19. And then here, the next one, you will get 23 because what you are doing is that you are summing 0, 1, 2, and 2, 7, 11. That rectangle, the leftmost two columns, leaving the bottom one. Okay, so that is 23. So this is how you go. In 52, this is 52 because here you sum everything up. Because when you are here, then draw a vertical line, draw a horizontal line, and then the area that is bounded by this subrectangle, you have to sum everything up. So that is 52. Okay, when you pre-process the data this way, and then now let's suppose the query comes. Okay, the query is the rectangle that is the bottom bottom right corner. Okay, so 0011. Let's suppose the query comes to find the total population on 0011. Okay, now how do you find? So in this one you will go and then pick 52. Okay, pick 52, and then you will have like this. You will have the original is 52, right? And plus I minus 1j plus j plus 1 minus grid I minus 1j plus 1. So basically what you do is that here you will go and then looking at these four numbers, the 40, 28, 39, and 52, you are going to answer. So when you look into these four the numbers, you are going to be able to get the total population in this area. So basically what is happening here, so if you look into 28, you know that the total population from here up to here is 28. Okay, and then the population up to here is 39, the below. So population up to here, these rectangles is 40, and then this is 52, right? So playing with these four numbers, you are going to be able to find the total population in this rectangle 0011. Okay, so here, since the rectangle is 0011, you might say that, oh, you are traversing all the elements of that rectangle to find an answer. But think about you have this whole rectangle as a population, and then you want to find the answer. So for that one, you will look at 52, you will look at 12, you will look at 0, and then you will look at 21. So from these four numbers, you are going to be able to find the answer. Okay. So this is how things work here. For example, here, if you look into this one here, the algorithmic trick is given. So you have this information 1, 1, 2, 1, 3, 1, 4, 1, and so on. So we have this grid, and then using that information on the grid, then you are going to be able to find. So the information is given here. For example, if you want to find so for example, if you want to find answer for this rectangle here, not the first column, just the second, third, and fourth, 11, 12, 21, 19, 24, 36, 23, 28, 40. Then if you want to find the population, total population in this grid here, leave the first row and last column, and then whatever remains, if you want to find that answer, then how can you find that answer is you have 40 minus 21 minus 11, 40 minus 21 minus 11 plus 23. And then when you do that, then you will be able to find that answer. And then that answer would be the number that you get. Okay. So this is how you will do the smarter one, but this problem this solution is still sequential. And then if you pre-process using order runtime and then you just answer one query, then you might not get see the too much benefit out of this. But if you answer many queries after you pre-process the data one time, then in amortization, then you are getting better. Okay, so this is order one work. So you can draw a picture or two to convince yourself that this works. And then I will say you this one. You can say that, oh, we might have another way to do it. Why do you do this way? Okay, you might say that. So a simpler approach, there is another approach to answer queries in order one time would be to pre-compute the answer to every possible query, right? You can do that too. For example, you have a grid, and then what do you do is that I want to compute answer to every possible query. I can do that because I have two-dimensional data. I can run the pre-processing of that data, and then I can compute the answer. So basically, what do I do is that, so it takes this much space, x square, y square. So length and height and width of the rectangle. So if x and y is height and width, then you will have order x square, y square space and the pre-processing time. And then if you put the answer this way, then you will be able to answer the query in order one time. But this does not need this much space. Whatever space that is available there in the grid, you can use that space and then just process the data. So the space is still order n. That is the size of the rectangle, not more. But this order x square, y square is too much space. And then you are actually computing all possible answers and keeping them somewhere so that whenever you need to answer that, then you can go and answer in order one time. And then which is not acceptable. And then this is compromising something. Although you can answer queries in order one time, you are losing on something else. So now here you have version 4 that is smarter and parallel. You can write this one. So here you use the first and second steps of version 3. As in version 3, you should create the grid that allows order one queries. Okay, so think about it. What did we do is that when we pre-process the query, we pre-process in order login time. And then for every query, we also spend order login time in version 2. Now the goal is to use the idea that we used in version 3 because you are finding an order login time. And then from that, try to somehow be able to answer queries in order one time, processing in parallel. So basically, in version 3, you were doing order and pre-processing time, but here you will do order login pre-processing time, and then you will be able to answer queries in order one time. So if you read the details here, then you will see how things work. And then we have another one, version 5, that is smarter and log-based. This is, again, you want to make version 4 better. So in version 4, you have to do a lot of grid copying. You have to copy data from the grid point to another grid point in the first grid building step. So this copying is a problematic because you have to have some other space and then you have to copy the data and then the problem. So what you want to do is that you, instead of copying the data, why don't you update the data in place there on the same grid? So if you want to do that, then you have to worry about the concurrent other threads. They come and then try to update the data at the same time there in that particular grid point. At that time, you have to now use some log-based mechanism to make sure that you are not losing the information that you wanted to store. Okay, so here the description is here. If you read the description, you will get to see what you need to do to make that happen. Okay, so there is a provided code. So the provided code will take care of parsing the input file. Okay, and it will perform the Mercator projection. So that is from spherical to the rectangle. You do not need to worry about that. And then it will put the data you need in a large array. It will put that information there. So now after that, you have to take charge and then try to solve the problem. So when you run the code, maybe you will give input like this. So you will so that your main file that you run is the population query. So that file is there. The template is given there. So you go and write the code there. So you have X and Y. So basically, and then X and Y is the number of columns, Y is the number of rows. You give the query input. And then when you say minus V1, minus V2, V3, then this one talks about which version that you are trying to run, because you have 5 different implementations. And then you have to give, okay, if I say minus V2, then I'm running version 2. That is naive but parallel. Version 3, sequential but smart. Version 4 is smart parallel. Version 5 is smart but using locking. Okay, so when you run this, then you will have a chance to evaluate them and then compare the performance between these different versions. So that's why this helps. You can answer it in a different way as well. You can choose to how to run the code there. That's up to you, but maybe it will give you a little bit more coherent way of dealing with the situation. For example, the output looks like this: Java population query send pop2010.txt. This is the input file. Okay, so if you have another input file, you can put it too. So that's why input file is also part of the query. And then you put you divide the rectangle. So basically you have the total rectangle divided into how many grid points. So you have to define those points. And then you are running version 1. So it will ask you, please give west, south, east, north coordinates of your query rectangle. So after you do this one, this one, it will compile the code. And then you have to give if you give the answer 1, 100, 500, then the population is this much. This is 100% population. That means it is counting the total population of the US. Okay. Now, after count the total population of the US, now this is time to give the query rectangle. That is the subset of the rectangle that we are talking about. So 1, 150, 500, if you give that, then you are talking about half rectangle of the total US population. So in that half rectangle, if you look at it, the population of that rectangle is this much, and percentage of total population is 8.9. So that half rectangle, I don't know what part it came into. That part, maybe it is covering most of Canada, and then and then some part of the US. So the total population that you see there, the US population is only 8.9%, although your query rectangle here is just the half of the total US rectangle. Okay, so this is very interesting. Okay, so you have here the experimentation. So here some of the things that you need to maybe be careful about. For example, here the program framework, it has to warm up. So that means all the libraries it will somehow prioritize the libraries when you run the code for many times. So when the library warms up, you try to see the better results. So so you can run the code a couple of times before you measure the time and everything related to the experimentation to see whether parallel program is working better or sequential is better. So again, the graphical interface here, this is optional. It is here, and then some information about how to run it. Similarly, here you have write-up questions, what to look into when you try to evaluate the sequential code with the parallel code, and then which one is doing better. So V1, V2, V3, V4, V5, these are just the versions that we talked about, and then you can go and compare them. So there are a couple of ones. If you try to answer these ones, then you will get into what we are looking for to see here. Okay. And then there are above and beyond too. For example, if you want to really go further and do it, that is parallel prefix. Okay, this is related to version 4. There is a parallel prefix coming, Earth curvature is coming, so you use a Mercator projection, and then you are not worried about that. But here, if you want to even make the answer accurate, then Mercator projection has some limitations. You can remove the limitation using Earth curvature. And then you have polygonal queries, as I mentioned before. We just handle rectangular queries. Maybe you can go beyond to see how to answer polygonal queries. For example, I give some shape. uh, you know this is not rectangle. Maybe I will go beyond the rectangle. Maybe I will give hexagonal, or maybe I will give concave or convex, or different kind of queries, and then how to answer those queries. So they will be a little bit trickier to answer, and then definitely you can go and then solve. So this is the total description about the project. So I will share this file, this project description. So I know that this project description is very long. Uh, you feel like, oh, how to read this one? I understand. But if you read this one from top to bottom, if you go through this document, you will have almost all information that is related to how to implement certain version, how to experiment, how to deal with the situation of mapping data to the rectangle, how to process the rectangle, where to keep data, how to evaluate them, how to see where the challenges and everything. So maybe it will help you to come up with a decision. So with that, I will stop here on the description about the project. So I will share the files with Dr. Gajar, and Dr. Gajar will share those with you, and then this description as well. And then if you like, you can work on it, and then you can actually contact me if you need some help in during the project, if you write code for that. So this is a way to learn Java if you haven't exposed to Java, because you will learn better if you are working on some project. Okay. So
Yeah.
with that,
Yes,
let me
thank you, Professor. A very detailed description of the project, how to define a real-time problem into converting it into a computer platform. Really, a lot of learning I also did from this particular project description. Thank you so much.
sure, of course, I will share the details with you so that you can share with the students. And then I'm of course available to answer anything that is related to this project.
Great, sir. Thank you.
Yeah.
So but now,
So
sir, we have 10 minutes to go. So if some of the thing is there spillover, we can continue in the next on the next day. So you can
yeah,
continue for 10 minutes or so. Yeah.
yeah, I will continue with that. But before I continue there, if there is any question right now related to this project, I will answer. You can write in chat box as well, or you can unmute and ask me, whichever way you feel better. Okay, you all are amazing. Either I described well, or
Now you described
anyway.
excellently, sir, as well as now demonstrated the kind of logic that you have looked into for all the versions. Great.
So let me start the open power. So I think this is what I would like to do starting today, and then we'll continue tomorrow and Friday. Ambika, that's a very good question. Yes, you can actually extend this kind of idea to solve some 3D data as well. Actually, in SPC and others, that happens. For example, three-dimensional array. Think about the three-dimensional array. When you think about that array, then you have to deal with now how to divide the job, right? So basically here, I mentioned, or in the project, I talked about how you go from one-dimensional to two-dimensional data. Now you are talking about how to go from two-dimensional to three-dimensional. And then when you go to three-dimensional, when you divide the data, and then instead of getting the subrectangle, you get the subcubes. Not maybe cubes like the 3D sub data. So and then you have to deal with that data. And then definitely you can write parallel code for that. Okay, so here the best way, I will leave that to you. Definitely not the sequential way, parallel way. So there are three parallel versions. So one is the naive parallel, and one is smarter parallel. So you might think that, oh, smarter parallel is better than naive parallel. I will say that. So version 4, and in version 5, you deal with some of the inherent technicality that comes behind the curtain. So that technicality is when you are working, dividing the data into subgrids and everything, then there is some complication on where you store that data. For example, every thread is working on some part, they have to store somewhere, right? And then when they store somewhere, they are replicating the data. Probably they are taking some more space. And then if you look into the memory hierarchy, if you look into huge number of data points, then that problem becomes vital. And then at that time, if you could do the in-place update, so the in-place update is you have the data structure that you are working on. So here the data structure is great. If you could update whatever calculation that you do into the data structure, you do not need another auxiliary data structure which copies the information, right? And then that helps when you have to deal with memory issues. And then that comes into picture when you have huge number of data points. We have just very, like 200,000 data points is not a big deal. I think in HPC and supercomputing, people really do not worry about these data points. They worry about billions of data points. And at that time, maybe version 5 is better. So version 4 and version 5, I will say. All right, here, maybe I will just put the context because I have exactly 6 minutes here. And then if you have any further question, you can actually send me an email. Okay, so and then I will get back to you. Okay. So here in OpenPower ISA instruction set architecture, what I do is that I will try to start. So this lecture has two parts. So the spillover we'll talk mostly tomorrow. I think I'll just put the context here. So the goal of this part is to introduce what is OpenPower ISA, and then there is architecture compliancy. You have the opportunity to just implement subset of the features that are provided by that architecture. Okay, and then there are some of the some of the fundamentals that were developed for future extensions or extensions that come beyond normal computers. Okay, so for example, you want to do SPC, high performance computing, you want to do supercomputing, and then for that one, you have to manipulate data in a very different way. For example, let's suppose you have one matrix, you have another matrix, and then you are doing the multiplication in that matrix. So this matrix multiplication is a very fundamental problem that comes into picture when you talk about high performance computing every time. And then if you write an algorithm, and then if you want to evaluate that algorithm to see whether that algorithm is performing well or not, they try to run that algorithm, or they try to run the architecture, or they try to use that architecture to see whether that architecture is able to solve some matrix multiplication problem faster than the previous architecture that was available. Okay, so we have BLAS, the benchmark. We have another many benchmarks. These are related to matrix multiplication, general matrix multiplication benchmarks, and then we run these benchmarks against those architectures, supercomputers, and everything to see how much benefit they give. And then that's how they compare the speed of the new architecture they design and then see, oh, this architecture is better than the previous architecture, right? So here, some of the features are provided so that you could actually use those features when you try to expedite the process of running this matrix multiplication. Okay, so I'm going to talk about that in the next part. In the next part, I will particularly talk about matrix multiplication assistance feature. So that feature will give you some idea on how can you use the architecture, that open power architecture, to do matrix multiplication. Okay, so here you could see that the Power ISA actually it became open. So why it's open? Because the instruction set architectures were mostly proprietary. That means, for example, if you think about Microsoft, if you think about Apple, if you think about others, they do not reveal their architecture to others. So they are proprietary, they have patents and everything. And then if you want to use that architecture, then you cannot really go and then look into their architecture and then try to build something based on their architecture because of that. So if the architecture is open, then you can use the architecture the way you want, okay, with some very limited restrictions, okay. So this open ISA developed by IBM, the open, Power PC, the architecture is completely open. You can go, you can see, you can use some subset of the architecture to design new system. For example, with the IoT devices, the Internet of Things devices and other devices, then you are now having so many different embedded systems. And then these embedded systems have different functionalities. For example, you design one embedded system to do certain job. And then if you are just doing some subset of job on that particular system, then if you have a very powerful architecture that you need to run, then probably because of the energy constraint, because of everything, that whole architecture, running that whole architecture may not be the ideal deal for that. So what you do is that you optimize just based on the requirements that you have, and the requirement you optimize in such a way that you save on battery, you save on different the computation. If you do not need some kind of computation, you don't want to do it. So that way you can prolong the battery life, as well as the system will work for a long time. And then so think about these doorbells, think about these other sensors and embedded systems where you have to worry about other factors, computation and everything, because they use too much energy. So this open power actually gives that benefit to the developers and benefits to the manufacturers of embedded systems and then sensor devices and everything, that you can use the patents, and then it will actually accelerate the innovation on these different sectors. And then so IBM actually is doing that through making their power instruction set architecture system completely open to the manufacturers and developers. Okay, so here you can use an user license, and then the Open Power Foundation, you can use that. So here, if you look into this one, Open ISA, the Open Instruction Set Architecture, was announced in North America Open Power Summit. So there is a big summit, happens every year. And then you have a final draft released by Open Power Foundation. It's a big foundation here. You can click on this link to go. And then now the latest version of Power ISA that is released is 3.1. There is a long history to that. So next time when we meet tomorrow, we'll start starting from there. So for today, it's 9 there and 10:30 here. So I will stop here. If you have some questions, I will take it for 5 minutes, and then after that, we'll close the session for today. Thank you, Dr. Gajjar. I will always stop here.
Yeah, thanks a lot for very detailed explanation about the projects. So once I'll receive the details from you, I'll share with the students. Definitely, they are at the end of the semester, so may not be practicing, but maybe during the semester break, I would see that some of them interested people can execute, and this is, in the true sense, really a good exercise to learn out the Java, the multi-core computing, all the aspects that Dr. Das has covered. Thank you so much, and wishing
Right.
you a great and great day ahead.
Right. I do not expect the students to finish that project. I mean, it takes time,
Yeah.
first of all, and then it has to be the mainstream project for them. So that is fine. But if they want to learn parallel programming and everything, then that would be the good practice for them to go and then start learning about it.
Sure.
Ambika, I will talk about sandbox when we meet tomorrow. I need some context for that. So we'll talk about that tomorrow. Yeah. So
Okay. Thank
uh,
you. Thank you so
all
much.
right. All right.
Bye.
That's all for today.
Bye.
Thank you.
Good day.